Let's move to the metallurgy session. We have a very distinguished speaker who has been with us since the beginning. Hi, Chris. He will speak about the evolution of platinum jewelry alloys from the 1920s to the 2020s. He is a very distinguished speaker on the technical issues at the Santa Fe and JTF symposia. He has more than 40 years of experience in the jewelry sector and in the World Gold Council before establishing his company in 2009, a PhD in metallurgy from the Surrey University. Before working on precious metals, he worked in the energy sector in the UK and Switzerland. He will speak about the evolution of platinum alloys in the 20th century, which was necessary thanks to the technology and metallurgy challenges to develop and improve jewelry alloys. Please, you have the floor.
Good morning. I'm going to share my screen. Just wait a moment. We all associate the early use of platinum in jewellery with the 1920s, about 100 years ago. Since then, it faded, and then the market really grew from the 1970s. And there has been much technological change. In particular, there has been a significant development of platinum jewellery alloys, and my presentation today reviews these changes. As I shall demonstrate, there has been a considerable development over the last 25 years. So let us begin with a quick review of the history of platinum. Platinum has only been known to Europe since the 16th century, with rumours of the existence of a white metal, platina, in Central and South America. Alloyed with the other 5 platinum group metals: palladium, rhodium, ruthenium, osmium, and iridium. And these were exploited by the pre-Columbian Indians of Ecuador and Colombia in northwest South America. Analysis of ancient trinkets indicates that iron and copper were also present as impurities. We note that it's since become used as a jewellery metal in Europe since the late 19th century, and that many jewellery alloys are based on industrial alloys. Its acceptance as a hallmarkable jewellery metal in the UK came much later in 1975. From this time, with its now much wider availability, platinum was promoted by the platinum producers as a rare, high-value jewellery metal, and platinum jewellery grew in popularity, mainly at 950 and 900 finest qualities, in Japan, in Europe, and the USA. Although some growth in demand began earlier in Japan in the 1960s for historical reasons linked to the ban on the import of gold until 1973. Platinum Guild International was formed in 1975 to promote the use of platinum in jewellery. This marketing and growth led to some alloy development, such as the platinum cobalt alloy for investment casting, and the use of gallium additions to produce heat-treatable alloys with higher strength and hardness. Initially, only a few alloys were on the market to meet manufacturing demands, and these were classified as casting alloys, general purpose alloys, and hard alloys. Huckle of Johnson Matthey reported on the development of platinum alloys to overcome production problems at the 1996 Santa Fe Symposium. He noted that platinum and its alloys had some different characteristics compared to gold and silver, notably its weight, hardness, and thermal conductivity, and that its alloys have a high density as well as very high melting points. Its high surface resistance leads to clogging or galling and high wear of saw blades, files, and machine tools. He notes that in Japan, platinum palladium alloys are in common use, particularly platinum 10% palladium alloy, whereas in Europe, platinum 5% copper is preferred applications. Platinum 5% cobalt is finding success. In the USA, he notes platinum 10% iridium is commonly in use as an all-purpose alloy, and that platinum 5% ruthenium is used where a hard, good machining alloy is needed. He also notes platinum 5% cobalt alloy is finding growing use for casting applications in the USA. Metz of Platinum Guild International also reviewed platinum alloys for jewellery at the 1999 Santa Fe Symposium, and this built on the information provided by Huckle. It sums up the alloys widely available and their application in jewellery at that time, with some comment on the new alloys being introduced, as we shall see in the table at a later slide. In this context, both Metz and Huckle noted it is important to recognise the different marking standards of various countries at that time. Metz noted European countries generally allowed only 950 fineness alloys, with some allowing no negative tolerance, some allowing a small negative tolerance, and others allowing iridium content to be counted as platinum within the 950 standard. In Germany, he noted that several fineness standards and alloys were allowed, as we can see in the table on the slide. In the USA, he noted that the standard for jewellery to be marked as platinum was 950 fineness, but the minimum amount of platinum allowed was 500 parts per thousand, with the rest of the alloy comprising the 950 parts per thousand total platinum group metals, and this with a zero tolerance. He also notes that 950, 900 and 850 fineness standards are allowed in Japan. This table shows alloys at 950 fineness that Metz noted. He notes, with regard to actual alloy compositions, that each alloy is made for specific manufacturing functions, as we can see on this table. For example, and there are different preferences in different countries. Table 2 lists the alloys in common or growing usage around the world with their function and countries of major use. He also lists separately a number of alloys that are specific to Japan. Metz's list did not record the platinum 5% copper alloy except for its use in Japan, which has been mentioned earlier as an alloy commonly used in Europe. METS does note that in the USA, the most common alloys in use are 950 platinum with 5% cobalt or ruthenium and 900 platinum, 10% iridium. However, in an updated version of this paper, the platinum 5% copper alloy has now been included. This table shows the rest of METS's table at 900, 850 and 800 finuses. As we can see, again, there are a range of alloys. These refer only to Europe and the USA and Japan generally. But in his book, Savitsky in 1984 notes that in the old USSR in Eastern Europe, only two 950 alloys are used. Platinum 5% iridium in Russia and platinum 4.5 palladium, 0.5 iridium in East Germany, the old German Democratic Republic. We can also note on this table some of the alloys that are specific to Japan. Let us look a bit at the technical aspects of these alloys. We note that at 950 and 900 finest qualities, there is a broad range of alloys available to the jeweller, each suited to various manufacturing techniques. All have a good white colour, although some may benefit from rhodium plating, for example, the platinum 10% palladium alloy, to give a brighter, whiter colour. The main differences between alloys lie in their hardness or strength and their melting ranges. Batani has examined the microstructure of several platinum alloys and notes that many alloys are single phase, as one might expect from examination of their phase diagrams, particularly at 950 and 900 finest qualities. We also note that some alloys are age hardenable and can achieve high hardness when in the aged condition, and we'll come along onto that in a little later. In this slide, I show some of the alloying additions, some of the alloying phase diagrams where we can show hardening by heat treatment is possible. This is the aging treatments. Some alloy systems show large areas of miscibility gaps at low temperatures. Examples are platinum gold and platinum copper systems. And we show the platinum gold phase diagram on the left-hand side of the slide. And we can see the vertical red line, which is equivalent to the 5% alloying addition. And we note this line intersects with the line of the miscibility gap. Platinum 5% gold is the example that we're showing here. And we can get an aged hardness of 300 Vickers, leading to better scratch and wear resistance of jewellery. The centre phase diagram, the platinum cobalt phase diagram, and ordered in platinum-free cobalt that just about touches the 5% cobalt composition line marked in red on the slide, suggests that possibly there might be some slight hardening available by age hardening heat treatments. The use of gallium, as we can see in the phase diagram on the right-hand side, shows the 3.5% gallium composition intersecting the limit of solid solubility, again demonstrating how we can use age hardening treatments to harden gallium-containing alloys. And its use forms the basis of several heat-treatable alloys, as we noted in the table. From the table of alloys, It is clear that some alloys are quite soft, with a hardness value lying in the range of 50 to 100 Vickers. Some have a moderate hardness value, hardness of 100 to 150 Vickers, and others are quite hard, with hardness in the range 150 to 350 Vickers. The higher values usually when in the age-hardened condition. In a recent study of customer complaints, it has been noted that the use of soft alloys is a significant factor in platinum jewellery becoming deformed in shape and bad scratch when worn by consumers, and wedding bands. Examples are pictured on the slide. The ring on the far right at the bottom has been deformed because the lady that wore it went to concerts very regularly and was clapping her hands very hard. And you can see the result. The melting point of pure platinum is 1796 degrees.
Vediamo il livello di fusione, vediamo quello dell'argento, del platino, vediamo che abbiamo delle range di fusione molto alte per il gaglio, come vediamo nella tabella. E queste leghe richiedono una buona attrezzatura in termini di fornace e anche una temperatura della lega piuttosto elevata. In generale, lavorare queste leghe non è un problema. C'è bisogno di una competenza particolare per avere una buona finitura e anche materiali speciali e diverse geometrie anche.
Tends to gall or adhere on the tool. The low thermal diffusivity of platinum alloys makes welding easier, particularly laser welding, compared to gold and silver alloys. Work around the turn of this century has demonstrated that microalloying of pure platinum and its alloys, with small additions of calcium and or rare earth metals such as cerium, samarium and gadolinium, typically up to about 0.3%, can increase hardness substantially. But such microalloys do not appear to have been commercialized by the jewellery industry, probably because they are not easily cast or recyclable. This table, table 3, shows the higher melting ranges and densities of platinum alloys. And we can note that gallium and indium additions, as we can see there, there's 3 alloys at the bottom of the 950 section, have lower melting temperatures compared to the other platinum alloys. And we note also the high density of all the alloys. The major manufacturing problems with platinum jewellery has been with investment casting. The high melting and casting temperatures require use of special phosphate bonded investment mould materials, and the poor melt fluidity requires use of centrifugal casting machines to obtain good mould fill rather than the modern gravity machines commonly used for gold and silver. The new generation of tilt casting machines are also suitable for platinum. The chief problem with platinum casting is getting defect-free castings, and there have been several investigations on the relative merits of different alloys, looking particularly at surface quality, form filling, and gas and shrinkage porosity. The general findings of these studies show that the platinum 5% cobalt alloy to be the best of current alloys, but it is still not ideal. Let us now look at progress in the last 20 or so years. There have been several studies to develop improved platinum jewellery alloys in the last 2 decades or so. These have focused on either stronger or harder alloys or improved investment casting alloys. Although alloys suitable for additive manufacturing or 3D printing have also been of interest. We will look at each of these areas in the following slides. Let us look first at stronger, harder alloys. The resistance of jewellery to abrasion and knocks, wear and scratch resistance, depends to a large extent on the hardness of the alloy. As noted earlier, a study of customer complaints showed platinum rings and wedding bands to be particularly prone to deformation of shape and to heavy wear, scratches and dents during customer service, i.e. whilst being worn, when they are made in soft or moderately hard alloys. Hard alloys tend to be difficult to work in manufacture, especially to set gems in mounts, and so it is advantageous if an alloy is relatively soft while being manufactured into a piece of jewellery that can be subsequently hardened to improve its durability while being worn by the customer. This can be achieved by age hardening heat treatment of suitable alloys after manufacture. This is a treatment involving precipitation of a dense dispersion of fine particles of a second phase within the matrix grains of the alloy. For platinum, it has been noted that some current alloys are age hardenable, and alloys containing gallium have been developed specifically for this purpose. The first was the platinum 3% gallium 1.5% indium alloy developed by Johnson Matthey, and others have followed, such as the HTA alloy developed by Imperial Smelting in Canada, and the S alloys developed by Steve Kretschmer in the USA. Wiesner, in a paper presented in 1999, discusses heat-treatable alloys and notes earlier work at Degussa, at Hafner, Johnson Matthey, and by Steve Kretschmer to develop heat-treatable quaternary alloys with many with melting ranges much lower than the conventional binary alloys, suggesting they all contain gallium and or indium additions. Such alloys are useful for their spring properties in springs and clasps, for example. Research carried out at Mintec in South Africa in 2005 has examined potential platinum alloy systems to identify suitable binary alloy systems that can be substantially age hardened. Over 20 alloying metals were studied in the preliminary trials at addition levels of 2 to 4%. From this work, the best alloy was a platinum 2% titanium alloy, which had an as-cast and annealed hardness sufficiently low to be easily worked and formed, but with subsequent heat treatment, the hardness value could be increased by about 90 figures. Interestingly, there are parallels here with the development of 990 gold, which is a gold 1% titanium alloy. The Mintec work does not appear to have been further developed into a commercial alloy, possibly because it does not show much advantage over existing commercial gallium-containing alloys. More recently, a harder general-purpose alloy, True Plat, has been introduced to the market in the USA by Hoover and Strong. It's a 950 platinum ruthenium gallium alloy that is not age hardenable. It has a high work hardening rate compared to 950 platinum ruthenium. And it has an annealed hardness of 180 Vickers compared to 130 Vickers for the ruthenium alloy. Look at improved casting alloys. The motivation here is to develop alloys less prone to casting defects, particularly casting porosity. Use of alloys with lower melting ranges to inhibit metal mold reaction is desirable too. Work carried out by Frié at Techform and Klotz and co-workers at FEM in Germany has focused on which alloys are best in terms of casting porosity, formation, form filling and surface quality, and establishing the mechanical properties of cast alloys. The use of computer simulation of the casting process has also assisted in optimizing process parameters in casting. Frié in particular has shown the benefits of a hot isostatic pressing treatment after casting in removing porosity from castings and improving the mechanical properties. What is particularly noticeable is the growing number of new platinum casting alloys that feature in these studies. And we will be talking about this in the next few slides. The alloy development started a little earlier than 2000 in 1997. Lanham of Engelhard, in a paper presented at the Platinum Day Symposium in New York, reported on a new investment casting alloy 950 platinum copper cobalt that combines the good properties of the platinum 5% cobalt alloy and the 5% copper alloys, and reduces the issue of magnetism in platinum cobalt alloy. Its as-cast hardness is about 119 Vickers, a little lower than the platinum 5% cobalt alloy. Porosity is still present, and it had a tendency to form a surface oxide on heating. Another alloy development was presented by Normando in 2000, in which he reported on a new 950 platinum hard casting alloy with an as-cast hardness of 160 to 170 Vickers, which is much higher than the platinum 5% cobalt alloy. Little detail is given on the composition, but the discussion in the paper points to it being a 950 platinum gallium iridium alloy. A further alloy development was presented by Grice and Cart in 2002, where the development of a platinum gold X alloy, Plat Oro, is reported as an alternative to platinum 5% cobalt. This has an as-cast hardness of 125 Vickers, a little softer than the platinum 5% cobalt alloy, but it is non-magnetic and has lower melting range of 1590 to 1629 degrees Celsius. Grice has since reported that the Plat Oro alloy is actually a 5% gold copper alloy, but is no longer commercially produced. Frié and Fischer-Bühner in their study reported in 2011 recognized the inadequacies of existing commercial casting alloys and widened their search to include 3 newer versions that contained undisclosed elements, which they designated as hard alloys. That is, they had a hardness of 175 or higher. The platinum cobalt X hard alloy with unknown additions appeared to show some promise. The platinum ruthenium X alloy is now known to be the platinum ruthenium gallium alloy from Hoover and Strong, and the platinum cobalt X alloy is a platinum cobalt indium alloy from Legor and is harder and non-magnetic compared to platinum cobalt. In 2014, Klotz and his co-workers at FEM in Germany utilized computer simulation of casting and thermodynamic calculations to optimize the process parameters of casting 5% ruthenium and 5% cobalt alloys, and was significant in that ternary alloys of the 950 platinum cobalt ruthenium alloys were explored, and they showed that improved form filling and surface quality resulted from additions of cobalt to platinum ruthenium alloys, the optimum amount depending on the casting technique used, centrifugal or tilt casting. In 2016, Mertz and Larg from Hafner studied 6 alloys which used tilt casting as opposed to centrifugal casting in their trials. 2 contained gallium or indium, and these alloys showed higher as cast hardness and were rated higher in terms of castability. Each alloy had different strengths and weaknesses, and the authors concluded that no alloy in their study was perfect, but that progress was being made. It is noted that Hafner's patented an alloy 950 platinum gold indium in 2013 with the use of iridium or ruthenium as grain refiners. The largest range of alloys was studied by Frier and Klotz in 2018. They also measured the mechanical properties and wear resistance of castings. They warned against the use of soft alloys in cast jewellery and noted pronounced microsegregation in gallium and indium containing alloys, which increased micro-shrinkage porosity. Hot isostatic pressing treatments after casting eliminated porosity and restored the ductility. They also noted wear was related to hardness, harder alloys wearing less. No new alloy met all the requirements for casting. These studies and alloys that they examined are listed here in Table 4. Note the large range of alloys studied. There are new alloys that feature and are mostly at 950 fineness, but there are 2 at 900 fineness. These all have a range of hardnesses and melting ranges. This slide shows the mechanical properties that were documented in this study. And for simplicity, I only show the hardness values for as cast and hot isostatically pressed alloys. So this gives us more detail. Ternary and quaternary alloys featured. There is a range of hardnesses, but no perfect alloy is defined. A more fundamental approach to improve casting alloy design has been undertaken recently by Professor Glatzel and his Professor Glatzel and his co-workers at the University of Bayreuth in Germany. They looked to develop an improved casting alloy of 950 fineness with the following requirements: a low casting temperature, a small melting range, a microstructure that is homogeneous, fine-grained in the range of 100 to 150 microns, and with low porosity. Hardness in the range of 155 to 170 Vickers for wear resistance and good ductility in excess of 30%. They also wanted good reflectance and a bright surface, and the use of alloying elements that are biocompatible and recyclable. In their study, their benchmark alloy was a 95% platinum, 1.8% copper, 2.9% gallium, which is a recent alloy development. They identified 25 possible alloying elements, and they ranked each element according to a suitability index. This comprised 4 characteristics: the maximum solubility in platinum, its hardness, the melting interval, and the liquidous change. They examined 2 sets of 5 alloys and tested them, and each contained up to 5 alloying additions. And these included elements such as aluminium, gold, copper, chromium, iron, iridium, manganese, palladium, rhodium, and vanadium. The compositions they studied are radically different from those alloys we've seen in the earlier slides. The compositions of the 2 most promising alloys are shown here on the table. 1A2 contains copper, iron, manganese, and chromium. The second alloy contains a little bit of copper, iron, palladium, vanadium, and yttrium. The hardness of these alloys, 164 for A2 and 165 Vickers for B2, is harder than the platinum cobalt alloy. And the benchmark alloy, the platinum cobalt gallium alloy they used, has a hardness of 225, quite a hard alloy. It begs the question, have these alloys been commercialized? And the other question that I beg is, with manganese and iron contents of these alloys, will it lead to a tarnishing problem? We saw that the use of manganese and iron when they were developing alternative white gold alloys without nickel and palladium, the Achilles heel was in fact tarnishing. So that's an interesting question we need to understand. Lastly, I'm going to talk very quickly about alloys for additive manufacturing or 3D printing. This is a technology that is attracting much interest in our industry, and the technique is known as selective laser melting. And this is where successive layers of alloy powders are selectively melted with a laser to build up a 3D model of the shape that's required. There is a lot of research taken on developing suitable machines, build techniques, and suitable alloy powders. It was very evident from the work that was done on gold for additive manufacturing that alloys need to be tailored to suit the selective laser melting process. You need to reduce the thermal conductivity and diffusivity and reduce the reflectance by adding alloying additions that better absorb energy and reduce local heat loss. This is because gold and silver have high thermal conductivities, and their high reflectance means that the energy tends to bounce off the surface rather than get absorbed. However, platinum and its alloys have much lower thermal conductivities, so making laser welding and selective laser melting much easier than gold and silver. There's particularly been a lot of research at Pro Gold on the selective laser melting of 950 platinum alloys by Damiano Zito and his co-workers. In a study they reported in 2014, they used a 950 platinum alloy but didn't give details of its composition. In 2015, they used an alloy which they said was a modified platinum cobalt alloy, a little bit different to the alloy they used in their 2014 study. In 2018, their study compared selective laser melting process to the same components made by investment casting, and in that they used a platinum copper gallium indium alloy. What became clear from all of these studies, manufacturing process, and there is no need to develop special alloy compositions for selective laser melting, which is in contrast to that what we've seen for gold. That is the end of my review of platinum alloys. So let's make a few conclusions. There's been an evolution and growth in platinum alloy compositions for jewellery over the last 100 years. The focus has been on developing alloys suited to the manufacturing process. There has been a major evolution in the last 20 to 30 years, particularly for investment casting application at the 950 finest quality standard. Investment casting of platinum alloys remains a major quality issue, particularly surface quality and porosity defects. It has been clearly shown that hot isostatic pressing after casting does remove porosity and improves the mechanical properties of castings. And lastly, the new technology of additive manufacturing does not appear to require special alloy compositions, unlike gold. Lastly, I'd like to thank Massimo Poliro and his staff at Ligor for inviting me to present at the Jewellery Technology Forum. And I'd also like to thank many friends and companies in the industry for providing me with information and allowing use of their pictures and tables, including Johnson Matthey, Ligor, ProGold, FEM, Platinum Guild International, Hoover and Strong, and Techful. Thank you very much.